Welcome everyone. We'll get started. So as Gordon said, we're talking about the unique configurable peripherals available on the 4300, which are our Cortex M4 based microcontrollers. So we're going to start off with, before we get into the peripherals, a quick introduction to the 4300. Probably some of you are familiar and some of you are not so familiar with that device, so we'll run through that quickly. And then we'll have an overview of the configurable peripherals, of which there are kind of three that are of particular interest that we'll dive into in some detail. And finally, I'm going to hand over to my colleague Bernard, who's going to take you through the State Configurable Timer, which is one of the peripherals we'll be talking about in detail. And it's just going to walk through the design flow, how to use this, how to use the tools that we have to get the best out of it, to show you some examples and hopefully a demonstration. Finally, we're going to try and leave 10 minutes at the end for a little bit of Q&A, always the most fun part. So the 4300. So it's a Cortex M4 based product, and it's probably worth pointing out, for those of you who are not familiar, NXP actually produces microcontrollers based on the M0, the M3 and the M4. So I think we're probably the only vendor in the market offering all three of these ARM cores in a microcontroller. The M0 is really the kind of entry point. It's meant for the 8-16-bit kind of microcontroller replacement. Very low cost of entry point, very low footprint, low dynamic power consumption, etc. Then we have the M3, which is kind of more the mid-range, a good mix of peripherals, good level of performance. And then finally the M4, which is a DSC, digital signal controller. That's kind of similar to a DSP, but it's more of a mix between a DSP and a microcontroller. So again, here's the families based on all these different M cores. So we got the M0, we've actually got two different devices in that family, the 11 and 1200. Really low cost low power consumption, and a lot of available on-chip memory options. The M3, kind of characterized by a lot higher performance, up to 150 megahertz, a lot of on-chip peripherals, USB, Ethernet, LCD controllers, etc. And then right up to the M4, the 4300, 150 megahertz, so really high performance. And it's also a dual-core device, and we'll touch on that a little bit later on. But it's got a lot of DSP extensions. So an M4 microcontroller is very similar to an M3, but it's got these extra DSP instructions and an extra floating point unit that really differentiate it and make it good for these microcontroller cross DSP type applications. So here it is. Here's the 4300. Loads and loads of peripherals, as you can see on there. So it's a very, very, very powerful device, aside from the powerful M4 and the M0. We've got UART, SPI, I2C, I2S, all the typical peripherals you'd find on a microcontroller. We've also got large amounts of memory, so a really nice dual bank flash available on the flash-based parts. Allows you to do highly secure firmware updates in the field. Large amounts of internal RAM, so if you really need high performance, load your algorithms into RAM, execute out of RAM. And of course we should mention the theme of this presentation, the advanced peripherals. We're going to go through those and list those in more detail, but let's not forget the things like the USB. So we've got a couple of USB 2.0 interfaces on here, both with on-chip PHYs. So that's actually a really neat feature. One of them is high-speed on-chip PHY, the other's a full-speed on-chip PHY, that you can also add an external high-speed PHY if required. So both of the USB interfaces can be used in high-speed mode. Obviously an Ethernet interface on-chip, LCD controller, we've got external memory controllers to hook up SD RAMs, so a very, very powerful microcontroller. It's also, considering the amount of power and the number of peripherals available, etc., it's actually, we think, really easy to use, primarily because of the ARM ecosystem. So loads and loads of tools out there, multiple vendors supply ARM tools, and you can take advantage of that. There's also free DSP libraries. So no need to write an assembler. You've got filters, FFTs you need to do. Absolutely no need to get bogged down in all these complex saturating math instructions, things like that. Take the DSP libraries free of charge, use those instead. Also a common tool chain. So you can design one project using an M4. Same tool chain is going to be able to support you on an M0 design or an M3 design. So really nice to be able to move through the different families with a common tool chain, common architecture, only one thing to learn. So it's also very, very flexible. And this is where we get to the main point of our presentation, I think. The flexibility really comes from the configurable peripherals that we've got on board. Three that we're going to go through in detail. The serial GPIO, what we call the SCT, the State Configurable Timer subsystem, and the SPI Flash Interface. We should also mention, of course, the fact that it's a dual-core device. We're not going to go into a lot of detail because there's another presentation done by some colleagues of mine that I think it was done earlier today, but there's another session tomorrow.
12:45 tomorrow.
12:45. So a lot more detail on the dual-core. We'll touch on it with a couple of slides just to explain the main concepts behind the dual-core, but not a lot of detail. For the rest of the presentation, we're going to go through these unique configurable peripherals. One more thing to note, I guess, and this comes up time and time again. This is an M4-based device, okay? But a lot of people probably don't actually need the DSP capabilities of an M4. So it's pin compatible with our LPC 1800 microcontrollers that are Cortex M3 based, and it's virtually peripheral compatible as well. So you can definitely design and lay out a board and move between an M3 based design to an M4, or from an M4 back to an M3. So a very, very flexible solution. Okay, so the configurable peripherals overview of, so let's start off very briefly with the Cortex M0. So I think a lot of people, the first thing they think about when they hear that it's a dual core device is, well, how does that work? Why have you done that? What's the idea behind that? And to put it simply, the real design intent behind it was to allow you to get the best out of the Cortex M4. So the Cortex M4 is a DSC. It's got these DSP instructions. It's got a floating point hardware unit. So it's really well suited to audio processing, control algorithms, running filters, etc. And it doesn't want to be burdened with the usual overhead of a microcontroller app, controlling real-time peripherals, etc. So we threw an M0 down on there as well to take care of that side of things. So that's the typical split that we see, is the M0 maybe taking care of USB, CAN, etc., things like that, looking after the real-time side of things, freeing up the M4 to do the processing, what it's good at. So how have we implemented this internally? Well, actually some really neat, they appear on the surface to be quite simple features. They actually make the solution as a whole very powerful. The first one is that both the M4 and the M0 are connected to the same bus matrix. And what that means is they can both access any piece of memory on the device. And seeing as all the peripherals are memory mapped, that means they can access any peripheral. They both have dedicated NVICs, so they can both respond to interrupts. Now the M4 can respond to any interrupt in the system from any peripheral. The M0 only supports a subset, but what we think the most commonly used peripherals. Separate clock and power control. So this is very, very powerful, because what this means is although the system will run up to 150 megahertz, you can actually choose to run the cores at different frequencies. So you can have the Cortex M4 running faster than the M0, or vice versa. And in fact, you only have to have one running at a time. The M4 can wait the M0, or vice versa. Very, very flexible solution. And finally, there's the shared memory available for IPC. So what we have, this shared memory is hooked up in a special way to both cores, and it allows us, or the M0, to post a message into this buffer, which could, in fact, wake the M4, or at least generate an interrupt on the M4 if it's not asleep. And that works in the other direction. So we've thought about one of the biggest challenges of the dual-core device, the IPC mechanisms. Hardware support for that, but also support in ROM. So the IPC is implemented as a software that's based in ROM, and we just provide an API call. So that's an overview of the M0. So now let's move on to some of the unique configurable peripherals. The first of which we're going to talk about is what we call the SGPIO, or the serial GPIO. Conceptually, actually really simple. Okay, it's just a GPIO coupled with a timer and a shift register. There's actually 16 of these. So there's 16 GPIOs, each of which has a separate shift register and timer. Fairly simple, okay, but it allows you to do some really, really neat things. And we can generate patterns in hardware, as we can see in the diagram. Very, very little CPU intervention. So it's perfect for bit banging applications. You know, before, if you've got some arbitrary waveform or pattern that you need to generate in the past, the only way really to do that is to sit in a loop, in a tight loop, set inputs high, low, etc. Very CPU intensive. SGPIO, configure a couple of registers, clock out the data, and you just get an interrupt when that data's been clocked out and reload, much like a UART. So really alleviates the CPU of this burden. So we said 16 of these. A couple of other features to mention about this. So this is data output. Can also clock data in. Allows us to emulate all sorts of different protocols. The final feature, output's got 3 states. Okay, so obviously you can enable the output, you can drive high or low, pretty standard GPIO. But you can also disable the output and put it into a tri-state mode for each bit that you clock out individually. And this allows, obviously, to emulate interfaces like I²C or other things that require the other end to pull the input down low. So to kind of get a better feel, there's a block diagram. It's not too scary. The top part is really the timer part of it. So if you remember, the SGPIO is a timer plus a shift register together. Top part's the timer. So it's got a pre-scaler, so we can control the rate at which data is clocked out or clocked in. This POS register, that allows us to control the number of bits that we clock out. Okay, so these are 32-bit shift registers. We can clock out from 1 to 32 bits. So very, very flexible. And in fact, we can actually concatenate a number of these blocks. So we can clock out 64 bits, 67 bits. We can hook up another one, 128 bits. So really, really flexible in terms of what data you can clock out, or again, clock in. The shift registers all have shadow registers. So much like in a UART, once the transmit's done, you get automatically reloaded from the shadow register. So the CPU doesn't have to respond in a particularly timely manner. It just needs to get the interrupt and reload that shadow register before the next amount of data has been clocked out. And finally, we've got the output enable register. So this is what I was talking about, being able to tri-state the outputs. So for every bit you clock out, if you're in output mode, you can control whether the output's enabled, so it's driving high or low, or whether it's tri-stated. So that's bit level control of the data that you're clocking out. So what do we use this for? Well, there's really 2 uses in our mind. Firstly, is a proprietary serial interface. So I'm sure you've all come across these peripherals. They're not quite SPI, not quite I²C, and you end up having to bit bang them. Okay, your CPU has to sit in a loop, set outputs high, low, etc. Read the state of an input. Very, very CPU intensive. Often have to have interrupts off, so you don't get dead spots in your waveform generation. Use the SGPIO instead. Set up the registers appropriately, and you really alleviate the processor from having to do a lot of this work. You're just going to get the occasional interrupt when your data's finished being clocked out, or when a new load of data has been clocked in. So very, very easy and effective way to emulate proprietary interfaces. But of course, also emulate standard serial interfaces, and this is really powerful, because although this is a chip when we have a huge amount of interfaces on it, we have a couple of I2S, a couple of I2C, a couple of SSP ports, but there's always an application that demands more. Okay, so if you have an application where you say, actually I need 3 I2S interfaces, well, okay, that's absolutely fine. That's what the SGPIO is there for. Kind of like magic, you get this extra interface. And we're going to make it really easy to produce these standard interfaces by having a library of examples available. So for all these standard interfaces that you find on our chip, or that maybe are not on our chip, but you find on other chips, there'll be a library of examples available to configure this peripheral to mimic that interface. So a very, very powerful peripheral. So the next one we're going to talk about is the SPI Flash Interface, or SPIFFY, as it's become known internally. Again, conceptually, really, really simple. It simply allows the Cortex M4 to view an external serial flash memory as a piece of read-only internal memory. Okay, now that sounds really straightforward, but obviously it's complex to implement. But it's a very powerful feature. Now, there's all sorts of SPI Flash memory out there. So there's obviously the standard SPI Flash memory we're all familiar with. But this was really designed, although it'll work with single SPI Flash memory, it was really designed to work with quad-SPI Flash. So this is exactly the same footprint as a standard SPI Flash, but actually has 4 data lines instead. So you can get 4 times as much data out of this in one go. And these flash memories are now becoming really, really cost competitive. So a really neat feature. So you have your external SPI Flash memory connected to your LPC 4300. It can be viewed as read-only memory, like we said. What that means is you can treat it like any other read-only memory. So one of the first things you think of is, well, I want to execute code from it. So yes, you can. You can execute code in place from an external serial flash memory. So I think that's a really, really, really neat feature. Now, obviously, there's a serial to parallel conversion going on there, so you're not going to expect quite the same performance as if you were executing this code from internal SRAM with a 32-bit data bus. But for me, the really shocking thing is it actually runs at 70% the speed. To me, that's very, very good performance, considering you're converting from a serial SPI Flash memory. You're running from serial SPI Flash memory directly. You know, you're not loading into this RAM for execution. This is executing out of the SPI Flash memory. So quite a lot of performance there. A couple of other ideas we've got for using this interface. Image storage. Okay, so a lot of applications, you're going to have an image that you're going to store in your flash memory, internal flash memory. You're going to load it into SRAM, and then you're going to output it on an LCD controller. So you're going to use up your internal flash memory for the storage of the image, and you're going to use up your internal RAM for your temporary storage, because that's where the LCD controller is going to get it from. So it's using up a lot of your resources internally. Here's the solution using the SPI Flash interface. We can eliminate storing it in on-chip flash, because we can store it in external serial flash memory. And also, because this can be viewed internally as internal read-only memory, it can be accessed directly by the LCD controller. So we can cut out both of these internal memory usages and get the LCD controller to directly access the image from a serial flash memory. Another application of it, NAND flash replacement. So a lot of systems will use a NAND flash or a NOR flash externally for bulk storage of your code. At boot up, that will be loaded into SDRAM, and it will be executed from SDRAM. So you're going to have these fairly large devices on your board. You're going to have to route a lot of tracks. You may have a 16-bit bus. You may even have a 32-bit data bus externally running all over your board to both of these devices. So big boards, complicated routing, a lot of board space, maybe potentially many layers on your board. We can eliminate the NAND flash memory and replace it with a serial flash memory. Okay? Even if we're not going to execute directly out of there because we need higher performance, that's okay. We store it in there, bulk storage, and we can transfer it very quickly due to the quad interface into SDRAM. So we can potentially replace a NAND or NOR flash memory, reduce your board size, reduce your cost and complexity of your design. So what devices do we support? Well, we said we support single SPI Flash, standard SPI Flash memory. Of course we do. And also quad-SPI Flash, okay, from all the major manufacturers, and we're adding to the list all the time and retesting. And when we say support for these devices, we mean both hardware and software, because obviously there's hardware that's got to interface with these flash devices. But then there's also software drivers in ROM that we test against these flash memories. So using the SPI Flash interface is actually very, very simple, because you just make it a call, and you basically tell it some characteristics about the flash memory you've hooked up, and assume it's one from one of our lists, then you can be guaranteed that it's going to work, and you just make a couple of API calls, and that will appear in internal memory as an internal block of read-only memory. So a really nice feature. And finally, for my section, what I wanted to talk about is the SCT. the State Configurable Timer subsystem. So this is what Bernard's going to go through in a lot more detail, the tool chain and the development flow for using this peripheral. But let's, before we get to that, we can have a quick overview. So the SCT is conceptually, like all of these peripherals really, again, is very simple. We can think of it as a timer with some state event logic coupled to the output of that timer. Allows us to generate a wide variety of waveforms with very little CPU intervention. We've got 8 inputs, 16 outputs, and a number of internal events and states. So maybe to describe exactly how that works in a bit more detail, we'll take a look at the block diagram. So on the right-hand side, you can see it's a standard timer, pre-scalers, up-down counter, match registers, etc. And really the right-hand side block, that's where a normal timer would end. And the output of that timer would be maybe an interrupt back into your CPU or toggle an output, etc. But what we've got is coupled into some state event logic. So it allows the whole block itself to take some conditional actions. Okay, so the first time the timer fires, it goes in there, checks what state it's in, takes a particular action, maybe reads an input, etc. Next time the timer fires, the state may have moved on. So this time, it can actually start another timer, take a snapshot of the value of another timer, etc. All without any CPU intervention. So very fast reaction to events and very low overhead on the processor. So a really simple application, just to give you an idea. Obviously, this traffic light system, this is trivial to implement in a microcontroller. Just writing C code. Okay, it's a no-brainer. It's very straightforward. So obviously, you've got the concept of state and events here. So we cycle through the lights for turning each one on for a certain amount of time, then moving on to the next one. So there's the idea of state, and the timer can drive that. But what's unique about this, and why the SCT is kind of a good fit for that, is you've actually got this button, you've got some input into the system. So normally if you're writing this, even if you used a timer, the handling of the pressing of that button would have to be taken care of in software. So you would have to change the way the timer is operating from your software. But the SCT, because it can actually has the concept of state and maintain an internal state and can look at outputs independently of the CPU, it can implement this traffic light kind of operation without any help from the CPU once it's configured. So it can change the way it operates based on the state of an input. So that's really one of the unique features of this timer. It can be totally independent from the CPU.
Ian already said that the SCT is in principle a timer combined with some state capabilities. I would extend this a little bit. In fact, it is a timer, but there is an idea behind that you can use this timer to realize things which couldn't be realized before. I mean, there are timers, there are pulse width modulators, there is software. You can do everything with this combination. But the reason to realize something like this in hardware is that the hardware can perform things in a very predictable way. If you have software, you always have interrupts which stop the processor doing things on this, doing other things for another part of the software. But if you configure this block one time, you can run it without any problem on the timing. So you can realize patterns, you can evaluate inputs with a very accurate timing without any jitter. So that's the unique feature here. And of course also that it is very configurable, so you can do more than one job with it. So we will see what we can do with it in this presentation. It's a little bit abstract to say state configurable timer. I want to compare it with something you might be familiar with, which is a standard state machine design with a commercial tool, a design flow which is available for years now, especially when it came to the protocol stack software in wireless. This tool, flow, of this of these applications are exactly the same. There is a graphical tool where you can draw your state machine. There is a section where you specify what the state machine should do in terms of timer periods, inputs, outputs, events, so whatever happens to the state machine. And the next step is that out of this definition, a code is generated, which is, for the professional tools, C code or whatever programming language. In the ASIC design or in the silicon design area, it's something which is put into VHDL, so you generate a hardware state machine with that. And in our case, for the SCT, we generate a set of registers, which will be programmed one time and will let this state machine run in hardware. So we quickly go to the differences between these two approaches. On the software state machine side, we have the first three things exactly the same way as for the SCT. There's a graphical designer, Telelogic Tau for software, for example, from IAR, there's a system which is doing that. On our side, we used a graphical tool, which is a Java tool, which is called FISIM. Then, on both tool sides, you have a kind of parser, compiler, interpreter, whatever, which checks your state machine implementation, which you have drawn, which checks the available resources, which optimizes maybe your state machines. On our SCT side, we have written a tool which is called FZM Parser. It's a command line tool which is just acting as a slave for a more powerful IDE. And the third thing is that out of this compiler, translator, whatever you might call it, there is a C-source file, text file, which is generated from this tool and which you put into your IDE project, in your application project for further processing in your project. But now we're coming to the differences. As I just mentioned before, the SCT can generate timings independent from the processor and from the compiler. It's just something which runs in hardware and which is all the time the same if you use a compiler from ARM, if you use the GNU compiler, whatever. It's a predictable system and it does not depend on any runtime of real-time code. And of course, performance is one of the things. If you run with a processor, okay, the processor is running on a specific speed and then you execute instructions, but you don't come up to a processor speed on the GPIOs. You only have, let's say, times 16 difference between the GPIO performance and the processor performance. This is different in the SCT. The SCT can act on a processor clock cycle. So any event which comes in, anything you want to put out, can work on a processor cycle. And on the LPC 4300, this is 150 megahertz. So whatever you do on the GPIOs which are connected to this SCT, you can work with the full processor speed. On the software state machine side, there is always a problem that you have jitter on signals. So if you want to put out something, let's say a pulse width modulator, you have a timing jitter because the software is not really predictable what it's doing. On our side, as I said, hardware, it's working as a charm all the time. But the advantage on the software state machine side is, of course, that it's scalable, whatever you like, within your available processor resources, your program memory. On the SCT side, you are, of course, limited by the resources which you have in the SCT. In the 4300, it's only one SCT implementation. There will be other platforms where we use maybe more than one SCT or a smaller SCT or a bigger SCT. So this depends on the number of applications our customers want to realize with it. And as I will show you afterwards, the programming of the state machine is, of course, a little bit abstract. That's why we created a tool chain. Otherwise, it would be a pain in the ass to write registers for the SCT and do exactly what you like them to do. So we took an available tool from the net, which is freeware. Has been made by a company here in US, Zimmer Design Services, and they called it FISIM. It was initially intended for ASIC designs. So we used this Java tool for drawing these bubbles and the arrows and so on. This tool generates an XML file as an output, which just describes what you have drawn in the state machine. Then we have an intermediate step where we take out the state machine information of the XML file, we optimize things, we restructure things, we check the available resources, and we convert this stuff into register settings for the SCT. Results in a few source files, SCT_FSM.c and .h, and these are inputs for a Kyle project, an IAR IDE, an Eclipse project. And there is a very small section which I have to supply to the IDE as well, which is another source file, example.inc and sctuser.h. There are a few things the compiler needs to know, which is, for example, the pin muxing for I/O. So this is not something which is fixed in the state machine tool. It is something which is fixed to your project. The graphical tool itself, Java, so in principle runs on every platform, but I think Windows is okay for nearly everybody. It's just used for drawing. All the text you see here on these bubbles, I mean, it's an add-on. It's something for your convenience, but it is not required to use this tool. You could use any other tool, apply the design you like, and then this intermediate step would perform your definition of a state machine drawing into source code. So we might develop this further to another level, maybe even professional level. This is just the beginning. We separated the graphical tool from the rest of the system, so this is something we can simply change and improve. And then comes the parser, fzm parser.exe, and as I said, this is taking the information of the state machine, converts it into something for the parser. It's just a text file conversion, taking out of the XML file what's needed, and the rest is left there. And then it restructures the state machine in such a way that the SCT resources fit to your state machine design. If they don't fit, the parser will give you a warning, or in fact it's an error because the stuff you did does not fit into the SCT. And there is also kind of optimization, because what you have drawn is maybe a not optimized flow for the SCT. So there will be a restructuring of events, of states, numbering of events. So this is done all internally. It's not something where you have to take care of during the drawing of the state machine. It's done in the tool. And due to that, it's in fact the real intelligence of this tool chain. I mean, the GUI is just a drawing tool. The IDE is an IDE, but in between this parser is the real intelligence. I mean, besides maybe the program in front of the computer, but that's not always not always the case. Yeah. The tool flow can be implemented in any of these IDEs, Microvision, Eclipse, IAR, whatever. You can even control it with a makefile. So it's not fixed to something we supply to you or try to get any license. So it's just freeware and open to everybody. What can you do with it? The traffic light has been mentioned before, and on the last trade fair in Nuremberg, we had in fact a traffic light which was running, so it was an eye catcher. I don't have something like this today, but I thought of an example where you can also think how this can be done differently. And I created a frequency counter with the SCT. A frequency counter is in principle a simple thing. It's just sampling on a signal and tries to find where is 1, where is 0. But the crux is you need to have accurate timing to get an accurate result, which is impossible in software. You can poll GPIO in software, but you can never make sure that the timing is all the time the same. So the SCT is perfect for that. If it is a real application, I don't know, but I could imagine that on some applications on the board there might be the need to measure a frequency somewhere here or there. So it's not something which is impossible in applications. I think it's something from the real world. The SCT samples on a clock signal. There's a generator here, the state machine is quite simple in terms of state machine diagram. It uses only one input, so output here, input into the board. There is one other output for debug reasons, but we don't need that. It's using 16 states and 16 events, which is just a definition by me. You could implement it differently as well. This is what it's doing. There's a clock signal with a specific period. The ratio is in this case 50-50, but it mustn't be. And there is the clock for the SCT, which is the oversampling clock, I would say. And at each edge of the clock signal, the SCT is doing something. Falling edge, for example, it's starting a timer, and on the rising edge, a capture event, it's stopping the timer. And you have a few clock cycles here, and it's doing this on any period here, 16 times, because 16 states, 16 events, 16 stop events, and after these 16 sampling periods, there is an IRQ generated from the SCT, and the processor can look at the samples which have been taken and calculate whatever you want to calculate. I show you the state machine of this application so that you get an impression what it means to do something like that. The Java tool looks like that. I'll make it smaller so that we can get the full view here. You can draw bubbles, you can draw arrows, you can specify some parameters. Here in the state machine there's always an entry state, that's by definition, it's an entry state. And on the captured one state, the state machine starts. First sampling, period over, stop event, next sample taken, and so on, up and down. Finally, you end up at state 16, which is captured 15, and then the interrupt is generated, which you see here, IRQ, sampling complete. It's pretty simple, it's pretty straightforward, but there are other applications which are not that straightforward, but it means that you have to understand how to design a state machine, not for the SCT, no. A state machine in general. If you generate C code with another tool, or if you generate code for the SCT, this is the hurdle here. You have to create a state machine. And our tool will tell you if it fits. That's easy. It's not a plug-and-play solution where you can say, oh, put things together and then it works fine. I mean, you have to create an idea, and you have to realize this idea with a state machine design. The code which is generated to show you the complexity of this stuff is in fact this one here. You have 16 registers for these 16 events, and there is a bit pattern inside. So I would say nearly impossible to do it by hand. So that's exactly the reason why we created the tool. And even apply changes to this one is hard to do. So it's easier to do it with the tool, recompile it, and test it again.